Today we're going to discuss how growth hormone is secreted and how it produces its effects in the body. 1. GH secretion. The hypothalamus controls GH release. The pituitary gland does not decide on its own when to release GH. Instead, it receives instructions from the hypothalamus, which is the control center of the endocrine system. The hypothalamus secretes a hormone called growth hormone releasing hormone, GHRH. GHRH travels through the hypophyseal portal circulation to the anterior pituitary. Once it reaches the pituitary, it binds to receptors on the somatotroph cells, stimulating them to release GH. You can think of GHRH as the accelerator pedal for GH secretion. 2. GH is secreted in pulses. This is one of the most important characteristics of GH. Unlike hormones such as thyroid hormone or cortisol, which are present in relatively stable concentrations, GH is released in short bursts throughout the day. Notice that most of the time, GH levels are very low, interrupted by occasional peaks. Why is pulsatile secretion important? Suppose a physician draws a blood sample between two pulses. The laboratory result may show GH equals very low. Does this automatically mean the patient has GH deficiency? No. The sample may simply have been taken between two normal pulses. This is why a random GH measurement is unreliable. Instead, clinicians usually measure IGF-1, which remains relatively stable throughout the day, or perform GH stimulation tests, such as the insulin tolerance test or glucagon stimulation test. Clinical Pearl. Never diagnose GH deficiency using a single random GH level. 3. GH secretion is highest during sleep. Peak levels occur around midnight during sleep. The largest burst of GH occurs during deep slow-wave sleep, stage N3. Typically, this happens about 1 to 2 hours after falling asleep. This explains why children with healthy sleep patterns tend to have better growth. Conversely, chronic sleep deprivation can reduce GH secretion and impair normal growth. This is one reason pediatricians emphasize good sleep habits. How GHRH stimulates GH release. Now that we know the hypothalamus secretes growth hormone releasing hormone, GHRH, the next question is, how does GHRH actually make the pituitary release growth hormone? When GHRH reaches the anterior pituitary, it binds to a specific receptor located on the surface of the somatotroph cells, which are the cells responsible for producing growth hormone. This receptor is a G-protein coupled receptor, GPCR. Once GHRH binds to it, the receptor activates a stimulatory G-protein known as GS. The activated GS protein then stimulates an enzyme called adenylyl cyclase. Adenylyl cyclase converts ATP into a molecule called cyclic AMP, which acts as an important intracellular second messenger. The increase in cyclic AMP activates protein kinase A. Protein kinase A phosphorylates several proteins inside the cell, leading to two important effects. It increases the synthesis of growth hormone by stimulating GH gene transcription. It promotes the release of the growth hormone that has already been stored inside secretory granules. In addition to activating the cyclic AMP pathway, GHRH also stimulates another signaling pathway that increases the production of inositol trisphosphate. This latter molecule causes calcium ions to be released from intracellular stores, raising the calcium concentration inside the somatotroph cell. This rise in intracellular calcium is the final signal needed for secretion. Calcium causes the secretory granules containing growth hormone to fuse with the cell membrane, allowing growth hormone to be released into the bloodstream by exocytosis. Therefore, both signaling pathways work together. The cyclic AMP pathway mainly increases the production and synthesis of growth hormone. The inositol trisphosphate calcium pathway mainly facilitates the actual secretion of growth hormone from the cell. How growth hormone acts on target cells. Once growth hormone has entered the circulation, it travels to its target tissues, such as the liver, muscles, bones, and adipose tissue. When GH reaches one of these target cells, it binds to a specific growth hormone receptor on the cell surface. Unlike insulin receptors, the GH receptor does not possess intrinsic tyrosine kinase activity. Instead, it belongs to the cytokine receptor family. Binding of GH causes two receptor molecules to come together, a process called receptor dimerization. This brings together two molecules of an intracellular enzyme called Janus kinase 2, JAK2. Once the receptors dimerize, JAK2 becomes activated and phosphorylates both the receptor itself and proteins called signal transducers and activators of transcription, STATs. The phosphorylated STAT proteins then pair up and move into the nucleus, where they bind to DNA and regulate the transcription of specific genes. These genes are responsible for many of the biological effects of growth hormone, including increased protein synthesis, enhanced cell growth, and stimulation of IGF-1 production by the liver. Because the signaling depends on activation of the JAK2 tyrosine kinase, we often describe GH as acting through a tyrosine kinase-associated JAK-STAT pathway, even though the receptor itself is not a receptor tyrosine kinase. Now that we've learned how growth hormone is secreted, the next step is to understand what GH does after it is released and how its secretion is regulated. Let's begin with the mechanism of action. Mechanism of action of growth hormone. Growth hormone produces its effects in two different ways. Direct actions. Indirect actions through IGF-1. It is important to distinguish between these because they affect different tissues and have different physiological roles. A. Direct actions of GH. GH has direct actions via a tyrosine kinase-associated receptor. This means GH binds directly to receptors on target tissues and immediately alters their metabolism without requiring another hormone. Let's discuss each effect. 1. Decreases glucose uptake into cells. One of GH's most important metabolic actions is reducing glucose uptake by muscle and fat cells. Normally, insulin promotes glucose entry into these cells. Growth hormone does the opposite. By decreasing glucose uptake, more glucose remains in the bloodstream. As a result, blood glucose concentration rises. Tissues become less responsive to insulin. This is called insulin resistance. For this reason, growth hormone is considered a diabetogenic hormone, meaning excessive GH can contribute to hyperglycemia. 2. Increases lipolysis. Growth hormone stimulates the breakdown of triglycerides stored in adipose tissue. This process is called lipolysis. When triglycerides are broken down, they release free fatty acids, glycerol. These free fatty acids are then used by muscles and other tissues as an energy source. By encouraging fat utilization, GH helps preserve glucose for organs that depend heavily on it, such as the brain. This is known as the glucose-sparing effect. 3. Increases protein synthesis. Growth hormone also promotes protein synthesis, especially in skeletal muscle. It stimulates cells to produce more structural and functional proteins. As a result, muscle mass increases. Lean body mass increases. Tissue repair is enhanced. This is one of the reasons GH is called an anabolic hormone. 4. Increases amino acid uptake. Proteins are built from amino acids. Growth hormone increases the transport of amino acids into muscle cells. By providing more amino acids inside the cell, GH supplies the raw materials needed for protein synthesis. Think of amino acids as the bricks and protein synthesis as building a house. GH delivers more bricks to the construction site. Summary of direct effects. So, growth hormone has 4 major direct metabolic actions. It decreases glucose uptake, causing insulin resistance. It increases lipolysis. It increases amino acid uptake. It increases protein synthesis. Notice the pattern. GH promotes the use of fat as fuel while preserving protein and maintaining blood glucose. B. Indirect actions of GH. Most of GH's growth-promoting effects are not produced directly by GH itself. Instead, GH stimulates the liver to produce IGF-1. IGF-1 is also called somatomedin C. Once released into the circulation, IGF-1 acts on many tissues. Stimulates growth. IGF-1 is responsible for bone growth, cartilage growth, organ growth, muscle growth. This is why children with GH deficiency grow poorly. Without GH, the liver produces less IGF-1, and normal growth cannot occur. Anabolic effects. IGF-1 also stimulates cell division, protein synthesis, tissue repair. Overall, it promotes the formation of new tissues and increases lean body mass. Important note: GH counters the effects of insulin on glucose and lipid metabolism but shares insulin's anabolic effects on protein synthesis. This sentence is very important. Let's break it down. On glucose metabolism. Insulin lowers blood glucose. Growth hormone raises blood glucose. Therefore, GH opposes insulin. On fat metabolism. Insulin promotes fat storage. Growth hormone promotes fat breakdown. Again, GH opposes insulin. On protein metabolism. Insulin stimulates protein synthesis. Growth hormone also stimulates protein synthesis. Here, GH and insulin work together. So GH is anti-insulin for glucose and fat metabolism, pro-insulin for protein metabolism. This is a favorite exam concept. Regulation of GH secretion. Now let's discuss what increases and decreases GH secretion. Remember that GH secretion is highly regulated because excessive GH or deficient GH both cause disease. Factors that increase GH secretion. 1. Deep sleep. The largest GH pulse occurs during deep slow-wave sleep. This explains why adequate sleep is essential for normal growth in children. 2. Fasting and hypoglycemia. Low blood glucose is a powerful stimulus for GH secretion. Why? Because GH increases blood glucose by decreasing glucose uptake, increasing lipolysis. Therefore, during fasting, GH helps maintain energy supply. 3. Alpha-adrenergic activity. Activation of alpha-adrenergic receptors, such as during stress, increases GH secretion. 4. Stress. Both physical and emotional stress increase GH secretion. Stress creates a catabolic state requiring additional energy. GH mobilizes fat stores to provide that energy. 5. Exercise. Exercise increases GH secretion. The more intense the exercise, the greater the GH response. This contributes to muscle growth, tissue repair, fat utilization. 6. Ghrelin, hunger hormone. Ghrelin is produced mainly by the stomach. Besides stimulating appetite, ghrelin also stimulates GH release from the pituitary. This is why fasting increases both ghrelin and GH levels. 7. Amino acids, especially arginine. Certain amino acids, particularly arginine, stimulate GH secretion. This is why arginine infusion is used as a GH stimulation test. 8. Sex steroids. Estrogen and testosterone increase GH secretion. During puberty, rising sex steroid levels enhance GH secretion. 9. Puberty. Puberty is associated with the highest GH secretion of life. Together, GH and sex hormones produce the adolescent growth spurt. 10. Chronic kidney disease, CKD. In CKD, GH clearance is reduced, and resistance to IGF-1 leads to compensatory elevation of GH levels. However, despite high GH, normal growth may still be impaired because the tissues become resistant to its effects. 11. Thyroid hormone, thyroxine. Normal thyroid hormone levels support GH synthesis and secretion. Children with hypothyroidism often have poor growth partly because GH production is reduced. 12. Short-term glucocorticoid exposure. Short-term exposure to glucocorticoids can transiently increase GH secretion. This is different from chronic exposure, which suppresses GH. Factors that decrease GH secretion. 1. Somatostatin. Somatostatin is the major inhibitory hormone for GH secretion. It is produced by the hypothalamus and directly suppresses somatotroph activity. Think of somatostatin as the physiological brake on GH secretion. 2. Beta-adrenergic activity. Activation of beta-adrenergic receptors decreases GH secretion. 3. Hyperglycemia. After eating, blood glucose rises. High glucose suppresses GH release because there is no need for GH to increase blood glucose further. 4. Obesity. Obesity is associated with chronically reduced GH secretion. Despite low GH levels, IGF may remain relatively normal. 5. Free fatty acids. Elevated circulating free fatty acids suppress GH release. This forms a negative feedback mechanism because GH itself increases lipolysis. 6. Hypothyroidism. Without sufficient thyroid hormone, GH synthesis decreases. Children with hypothyroidism therefore often have growth failure. 7. IGF-1. IGF-1 provides negative feedback. When IGF-1 levels become high, it signals both the hypothalamus and pituitary to reduce further GH secretion. This prevents excessive growth. 8. Pregnancy. During pregnancy, the placenta produces placental growth hormone, which largely replaces pituitary GH. As placental GH levels rise, secretion of pituitary GH falls. 9. Increased age. GH secretion naturally declines with aging. This contributes to decreased muscle mass, increased body fat, reduced bone density in older adults. 10. Chronic glucocorticoid therapy. Unlike short-term exposure, prolonged glucocorticoid therapy suppresses GH secretion and inhibits growth. This explains why children receiving long-term corticosteroids may develop growth retardation. 11. Glucose. After meals, elevated glucose suppresses GH release, reinforcing the effect of hyperglycemia. Now that we have discussed the physiology of growth hormone, its secretion, regulation, and mechanism of action, we'll move on to its clinical relevance. Understanding how GH behaves in different diseases is extremely important because GH levels do not always reflect its biological activity. In some conditions, GH is elevated, but its effects are reduced due to resistance or impaired IGF-1 production. We'll discuss 3 clinical situations. Diabetes mellitus. Malnutrition. Disorders caused by GH deficiency or excess. Clinical considerations. 1. Type 1 diabetes mellitus. GH levels are increased. Let's begin with type 1 diabetes mellitus. Type 1 diabetes is characterized by absolute insulin deficiency due to autoimmune destruction of the pancreatic beta cells. Normally, insulin suppresses GH secretion indirectly by promoting the production of IGF-1 in the liver. When insulin is absent, the liver cannot produce normal amounts of IGF-1. Low IGF-1 removes its normal negative feedback on the hypothalamus and pituitary. The pituitary compensates by secreting more GH. Therefore, patients with type 1 diabetes usually have elevated GH levels. However, despite the high GH concentration, its growth-promoting effects may be reduced because hepatic IGF-1 production is impaired. Clinical significance. The elevated GH further worsens hyperglycemia because GH decreases glucose uptake by muscle and fat, increases lipolysis, stimulates gluconeogenesis indirectly, increases insulin resistance. This contributes to the difficulty in controlling blood glucose in untreated type 1 diabetes. 2. Type 2 diabetes mellitus. GH levels may be increased, normal, or decreased. Unlike type 1 diabetes, type 2 diabetes is characterized primarily by insulin resistance rather than absolute insulin deficiency. Because patients vary in obesity, insulin resistance, insulin secretion, duration of disease, GH secretion also varies considerably. Some patients have normal GH, mildly elevated GH, or even reduced GH secretion. There is no single characteristic GH pattern in type 2 diabetes. 3. Malnutrition. High GH levels with low IGF-1 levels is a classic concept known as growth hormone resistance. Let's understand why. During malnutrition, the pituitary continues to release GH, and in fact secretes more GH than normal. However, the liver lacks sufficient nutrients and energy to synthesize adequate amounts of IGF-1. As a result, GH levels increase. IGF-1 levels decrease. The body becomes resistant to the growth-promoting effects of GH. Why does this happen? The body is trying to conserve energy. Growth is an energy-consuming process. During starvation, the body prioritizes survival rather than growth. Therefore, GH shifts its actions toward fat mobilization. Growth is temporarily suppressed because IGF-1 production falls. Clinical consequence. Children with chronic malnutrition often have poor linear growth, delayed puberty, low IGF-1 levels, elevated GH concentrations. 4. Poorly controlled diabetes. Here, we find high GH levels with normal or low IGF-1 levels. This situation resembles malnutrition. Poor glycemic control reduces the liver's responsiveness to GH. Consequently, the pituitary secretes more GH. But the liver fails to produce an appropriate amount of IGF-1. This phenomenon is called GH-IGF-1 dissociation. What does dissociation mean? Normally, high GH should produce high IGF-1. In poorly controlled diabetes, GH is high, but IGF-1 remains normal or low. The expected relationship between the two hormones is lost. This is referred to as dissociation. Conditions associated with GH disorders. Now let's discuss diseases caused by abnormal GH secretion. 1. GH deficiency. Short stature. In children, GH deficiency results in reduced longitudinal bone growth, delayed skeletal maturation, decreased muscle mass, increased body fat, normal intelligence. These children are usually proportionately short, not intellectually impaired, with delayed bone age. In adults, GH deficiency presents differently because growth has already stopped. Adults may develop increased fat mass, reduced muscle strength, decreased bone density, fatigue, impaired quality of life. 2. GH excess. Growth hormone excess produces different diseases depending on whether the epiphyseal growth plates are open or closed. Before epiphyseal closure, excess GH causes gigantism. The patient becomes abnormally tall because long bones continue to grow. After epiphyseal closure, long bones can no longer lengthen. Instead, GH causes enlargement of soft tissues and membranous bones, producing acromegaly. Typical clinical features include enlarged hands, enlarged feet, coarse facial features, frontal bossing, prognathism, macroglossia, hypertension, insulin resistance, cardiomyopathy. The most common cause is a GH-secreting pituitary adenoma.